So in class, a number of times I've talked about that you should be calibrating your motors and your sensors. There was a few slides on it, but we never really dealt with it. So I thought I would show you how I did it. I'm going to go over this quickly, showing you something in Excel, and then I'm going to share the Excel file with you because I don't want to spend like an hour talking about this. I'm not confident that that many people are even going to watch this or pay attention, so it doesn't seem like I should go into a lot of detail, but you'll have the Excel file, and if you have questions, you can talk to me about it. So the point is, you need to know something about your motors, and that could be informal or more detailed. And this is one way you could do it. And the one reason to look at this and spend some time on it would be that it's an introduction to Excel. If you haven't really used Excel, you're going to probably have to at some point, and it's a really powerful tool for manipulating data pretty easily. Anyway, so what I'm suggesting as a minimum is that you open up Excel, type in some values. I started at 120, stopped at 60, because one thing I found in my calibration is that my robots top out, my motors top out at 115 in the counterclockwise direction, 115 degrees, and at about 70 degrees in the clockwise direction. So that's one of the big things that you would want to, it's very simple, but that you'd want to do by calibrating. Let's say I didn't know that, and I was later trying to write some code and test it with my robot, and I was putting in 0 to try to go as fast as I could in the clockwise direction, and 180 to go as fast as I could in the counterclockwise direction. And then I said, well, I want to slow it down a little bit, so I'm going to go to 10 degrees and 170 degrees, and I would flash that, and it would go at the same speed. And I would think, okay, well, maybe I'm doing something with my code. I would be looking around. And maybe I'd go, well, okay, look, I'll try 20 and 160 or something. The same thing would happen. I would probably get pretty underconfident as I would try that a few times and say, well, it's got to be something wrong with my code because there's no way these motors are not going slower yet. But they are. It's just simply that at least my motors, and I've tested 2 or 3 robots, they were all like this. The specs say, if you look up the code, it says that 90 is off, 0 is full speed clockwise, and 180 is full speed counterclockwise. And I'm saying that's just wrong, that actually full speed is, I mean, that's right, you can put it at 0 and you'd be at full speed, but you're already at full speed at 70. Anyway, so that's why I'm going from 120 to 60. But what I'm saying is you just would type in some values. I've got right and left because I also want to figure out if my motors, if I put in 90, 100, and 100, will my robot go straight? If not, I'm going to have to calibrate it. I'm going to change. I'm going to have to figure out either I have to adjust the physical build of the robot. And I said in class, I think that would be difficult to do. You could, because you could try to push the wheels to be different angles, or adjust the camber or toe is what it's called if you look in the slides. And I think that our robots are not set up to do that easily. That they're pretty rigid. So I think that if you're not going straight with when your motors are set at the same speed, you're going to have to adjust the speed of one of the motors to straighten out the robot. What I determined, so you'll see then that I'm going from 120, 90 should be stopped to 60, and I did tests of 1-second intervals. So I put that note in here. And what's another point I'm making here is that so you could be playing around with your robot, your motors, and your robot chassis, and saying, okay, yeah, I've got the code to go. I'm going forward now, and it's above 90. I'm going backwards or counterclockwise. It's less than 90. Great. Oh, yeah, it's not going straight. You can play around. Oh, yeah, I think if I adjusted this much, that seems to work. Do some tests, and then you just move on. Well, you don't really have any data to help you actually do fine tuning in your code, or even just you may not remember exactly what was going on. I'm suggesting by opening up Excel, and as you're experimenting with your robots, you keep track of the data in Excel, then you'll actually have usable data that you can use in coding that you can refer to for different things. So what I did here was I'm setting a left and right speed, or speed in this case is in degrees, And then I have another column that's basically speed in inches per second. And I have a note here, so I can go into Excel and say I can insert a comment, and that's how I did that. That's how I put in this little, it shows up here, it's a comment, and I could just say 1 second intervals um, to remind myself that I only that I was running the robot for a second. Now I might think, well, the robot takes a little while to get started, so maybe I ought to go 5 seconds, and that way, it'll sort of average out that it'll get up to speed, and then I have a more accurate measurement. I kind of don't think that's true. It seems like the robots, they get going right away. So I thought a second was fine. But I don't really care if this is accurate because I'm just doing this to show you. I'm not doing the project myself. But anyway, that's why I did that. And then I made a notation here. Once um, I did this full test of, I flash code with each of these values for both, and I experimented with whether or not the robot was going straight. I just really couldn't get the robot to go completely straight. And it seemed to me that when I would try to adjust it, like in other words, if I went from 80 to 80 and 79, then I would adjust it too much. So even just 1 degree would send me too far, would be too big of an adjustment. If I went to zero point 0.5 or 0.75, I had the same results. So it didn't seem like for me increments of one, anything between less than 1 degree of adjustment didn't seem to be possible. Now I don't know if that's true. I didn't research to see what if you can um, if 1 degree and 1.5 degrees are different speeds or not in terms of what the specs of the robot. Didn't seem like it was to me. So I just made a note to myself that I really can't get these to go perfectly straight. It's not terrible, so I thought, okay, well, I'll just leave it. I'm gonna code them with both motors going the same speed and saying that straight, even though it's not completely true. And again, I have a note in here. That's going to be something that I can refer to that reminds me I did do that test. If I have other group members or whatever, they can look at this and see what the results were. So it's just really good practice to get into where you're starting to keep track of your data. By the way, what did I do here? This is just so these two cells are merged and centered. That's how I combine. So I had a right and left motor. Uh, I could create a cell above it that merged and centered that lines up then that heading with the two columns below it. Um, I selected all of my data, went to this section here in the font layout, and I said select, what's it called? All borders. Then I selected it again and did a solid, thick outside border. That's how I got that. And you can go further with this, however you want to do it. Um, anyway, so now that's my basic data. What can I do with that? How can I use that to help me with coding or to help me with my project? So here's that same data laid out differently, and then I've got a bunch of other stuff going on around it. Now again, I'm going to go over this quickly. I'll pause on cells so that you can see the formulas that I've got in there. So therefore, when you have this Excel file, you can use this video and the Excel file together to understand what's going on if you want to. Of course, ask me questions if you're interested. This is not a requirement for the class. It's just me showing you something that I would do if I were you in Excel. So the first thing I did was I took this basic data and I organized it because I saw that between 90 and 95 is my zero zone. So it is my 0 inches per second. So I'm stopped. That's interesting because you would think if there was a range and we're saying 90 is off, then it should be like 93 and 87 or something like that, right? That's not the case. It seems, at least with these motors I tested here, um, between 90 and 95 is off. So that means if I'm my well, let's jump forward. Then I found that, like I said, about 70 was where my robot topped out in speed, and so that's 20 above the upper end of the off section down here. So that's 20 degrees. And down here it's the same thing. 115 degrees is the topping off point. But since I started off at 95, um, if I thought 90 was where stop begins, then that would confuse me. That would I would my relationship between off and forward and backwards would be different. So this is a reason why you would do this. This is much clearer to me now how this motor is functioning as far as speed goes. The other thing is that I went obviously at the beginning I did little increments just because I wanted to see how quickly the speed changed. Once it got going, I basically just went in 10-degree increments, and then when I got to where I topped out, well, basically if I went if I got a speed per inch and then I went to the next measurement and I got the same speed per inch, then I surmised that I was at the top speed. So that's why I don't go all the way to 0 or 180. Okay, so I did that for my motor speeds. I already told you that that I decided just to leave to say that right and left are the same speed to go straight, but that's not really true, and I made a note of that. Um, But let me talk about a few other things here. So then, I tend to, for example, if I go to view, I can turn on the grid lines are off. I turn them off usually when I'm at this point because I'm trying to make what I would call a GUI, a graphic user interface. I want to make something that looks like a physical object as much as possible, or even just something that is as clear as I can make it graphically to someone who's trying to understand the chart. So that's why I take some time. I, give it a title. I did that thing here that I showed you before, the merge and center. If you just select you type. So this robot calibration is just in this one cell right here. If I select all these cells and I say merge and center, then it centers it within that group, and those are now one big cell. I have a terms section. It's always a good idea, even if it just seems really straightforward, to define the terms you're going to use, and then you're going to always want to have abbreviations. So that's what I'm doing here, so that when I have RT over here, I know it's right, and maybe that's obvious, but I think it's good to be pretty direct with these kind of things. Then I have a spec section. For example, actually this is even wrong. Well, no, I can leave it this way now, but I don't have any place I don't think where M1 is called out. In my text, in my code, I've started saying ML and MR. Because I don't think motor 1 and motor 2 really is very helpful as descriptively. Oops, did it backwards. Anyway, it's up to you. Just explaining this. I left this blank in case I did want to have some kind of calibration, like add 2 to the left motor speed or degrees in order to make it go straight. I have a record here of the minimum, the maximum over that I got. So it's just a way to quickly summarize my data. I have specs on the chassis width, which we would need when we do the turning radius. I think I'll talk about that last. So basically I have some specs, some terms, then I have my data here, and then what I do with the data? Well, I can make a simple calculator with it that allows me to figure out speed per second for any degree setting. And lets me, if I want to go at a certain degree setting and I want my robot to go a certain number of inches, how far should what time setting, delay time setting should I put in my code? So that's what I'm doing here with these little equations. So how did I do it? Well, first I created a chart. So if I go to Insert, Charts, Charts is in this section. I'm going to use a scatter plot. Scatter plots are charts that allow you to plot X and Y variables. And so I just selected that. Oops. This is very confused because I'd selected this whole chart of data, and this Excel is trying to guess what I'm trying to do with all that data. I don't want to do that, so I'm going to delete that. I've not done anything selected. I'm going to go Insert Scatter Plot, and I'm going to select data so let me just quickly show you how you do that. You right click on the chart, say Select Data. So if I say I want to have Actually, I'm not going to give it a title. Doesn't matter right now. I'm just going to throw some. I'm actually not even going to do it. I'm just going to show. This is how you put in a data series. So let me show you data series in the charts that I've got here. I'm going to delete this chart. Um, so select data. I've got degree trend 1 and degree trend 2. Trend means trend line. What these are, so for trend 1, I went from 0 to where I topped out, right? And so that's in the counterclockwise direction. And then my second one is in the clockwise direction. So I've got now two data sets in here. So that's these little yellow and gray dots. Um, so they're plotted now in a chart with speed as the x-axis and degrees as the y-axis. Then I added a trend line. That's what these dotted lines are. And so to do that, I selected a data set and said add trend line. Now it's formatting it because it's already there. I come in and I can choose a trend. So what a trend line simply is what it sounds like. It's that you have some data and you say, what's the trend for the data? Is there an equation that I can apply to this data that will describe it? Um, in this case, it's, I could choose anything I want, but it seems that this is pretty linear, so I decided to choose linear. That was a good description. This dotted line is going through my data set, and that okay. Okay, so I did that, and then I displayed the equation on the chart, which is what this variable is, and that's this equation here, and this one here for each of these data sets. Then with that, I can come up here and create and use that equation to create a calculator. So I'm saying if I put in, if I want my robot to go 80 degrees, what will its speed be? Well, I can use this equation. So if so my speed is x, right? Is the x value in this chart. So then if I solve for x, um, which is the, and see if I click on the let me do it again. If I click on the cell, whatever I'm putting in that cell shows up here in the formula bar. Equals is an equation in Excel, so now I've got a formula here, equals, and I'm using this, I'm solving for x using this, this is the equation of a line down here, solving for x, and therefore I'm going to output, given any degree I put in here, I'm going to output a speed. All right, so if I change this to 85, I get a different speed. Um, Now, if that's confusing, it'll be much clearer if you look at the file compared to this, compared to this video. And if I just keep talking, it's just going to get more confusing. So, and then you can ask me questions. But the point is now that I have, rather than having this blunt chart over here, I've got a calculator where I can put in very exacting degree calculation or degree settings and get a more exact speed that's an approximation based on this, the data that I've collected. Then I can just say, okay, well, I want to know if I want to make this robot go, if it's going 84 degrees is the speed, which is 5.1 inches per second. I want it to go 12 inches. What is my time delay in my code? Well, then I'm just going to take the inches divided by the inches per second to get seconds, right? So I just divided this cell by this cell, and I get the output. So I have a simple calculator. Did the same thing for clockwise as I did for counterclockwise. Um, and then I can, anyway, I'm just saying I can use this in my code if I want to. Or maybe not. This is just showing you something that's possible. I'm not sure you'd ever use it. Let's look quickly then at turning radius. So what is turning radius about? If I made this quick little drawing up sketch of it, basically we're saying it, with our specific, well, turning radius is if you have something, you have a vehicle, and typically the turning radius means what's the tightest turn it can make. So for this robot, the tightest turn it can make would be its wheelbase, which is the distance between the two wheels, times two. Because as you can see here, if I keep this wheel stationary, which is, or this wheel stationary, and it's at 90 degrees stopped, and let's say I just set this one at 80, no matter what no matter what I set this at, it's going to go in a circle And that circle is going to have a diameter of 8 inches because 4 inches is the wheelbase. Um, so its turning radius would be 4 inches. But for our purposes, we may want to know, so that's like the official turning radius. But when you say turning radius in this context, we may want to be able to figure out, well, what if I want the robot to turn in a larger circle than that smallest one? How can I know how to code it? Well, then I could do an experiment where I set different. So I said now instead of this being stopped, I'm going to set this at 85. Keep this at 80, and run an experiment and see how big this circle is. It's going to be larger because they're both going to be moving forward. Um, so that's what I did here. I just said, okay, I'm going to keep my right motor always at 80. I'm going to start my left motor at 90 and then just slowly slow it down. And I'm going to keep track of my turning radius. And I'm just measuring that. Oh, and by the way, I don't know if I said that over here. The way I measured all this stuff is I put a piece of tape on the ground, and I ran the motor. I flashed the code, ran it for a second, used a tape measure, see how far it went. Pretty simple. Um, so the same thing here. I just set the motor down, set the robot down, ran the code, and I had to adjust the code length so that I always wanted to go at least in a circle once. And I measured with a tape measure what the turning radius was. Um, and so then again, I can plot this data in a chart. I'll show you the chart. Select data. Um, I'm just saying, I'm plotting the difference um, in I'm plotting the difference in motor speed, so between the right and the left, by the measured turning radius. And then that gives me an equation here that I can use to calculate a turning radius. So again, I'm just showing you this quickly so that you can come and play with it yourself if you want to. So this is my experimental turning radius using this equation. By the way, this is not linear, so I just used a different, what did I use here? I used the polynomial setting. It seemed to match pretty well. Um, there's obvious mathematical reasons why that would be true. It works better than the exponential, or definitely it's not linear, I'm sure. Um, it's not a power relationship. So polynomial second order will work for reasons that maybe should be clear algebraically to you. All right. Anyway, so that's how I can get then. I can estimate a turning radius. So if I said I want this my robot to whenever it comes to an obstacle to turn really quickly, or I want it actually to turn more slowly and have a larger arc, this would help me code that, or at least have a starting point. By the way, another thing I did was I honestly, so this is the turning radius equation we were given in the slides, and I don't understand the derivation of it. Maybe somebody else, maybe it's obvious to you. Um, and also, it doesn't work as far as I can tell, because of what I'm saying. You see, if I put in a wheelbase of 3 and a speed of 3 for one of the motors and of 0 for the other, so now I'm in this category where I'm trying to make this thing just turn around as quickly as it can. The smallest um, turning radius you could have would be its wheelbase, and using the equation they gave us. Um, Sorry, I forgot it already adjusted this. So let me come in here and do the actual equation they've got for us here. Using their equation, so I'm saying I'm keeping one motor stationary, the second I'm moving at whatever rate. They're saying I have a turning radius of half my wheelbase. That's not possible for our robot. It seems like they're thinking that they have a wheel or that they're turning around the middle of the robot. Like if I was turning around this point here, then yeah, I would have a turning radius that was half of my robot. Um, this may be the robots before had, yeah, I'm not exactly sure when that would ever be true. Um, anyway, so I just adjusted this. So I used this to prove this to myself, that this didn't seem to work, and so then I adjusted the equation, just made it, I didn't divide it by 2, so that what was common sense worked out for me. And then it turns out that it's pretty accurate when I compare. So this is my experimental and this is my theoretical. This is the equation from that was given that I adjusted by not making it divided by 2. And we can see if I come in and I adjust my speeds, I keep pretty close to my theoretical with my experimental. So that's, it's not perfect by any means, but it's in the ballpark. So I think that's a more accurate theoretical equation for our robot build. All right, that's all I have to say about this. Let me know if you want to delve into more into Excel or ask me questions about this. Fine. I mean, I'd be happy to show you or talk to you about it. But the general point, if you've come this far, I would assume actually you do want to do that because you've listened to this whole thing. But I'll just make a general point, which is you need to understand how your motors and sensors essentially function, and a good way of doing that is collecting some data. It'll help you code, and you can do that in a simple way or a more complex way, but you want to do it in some way um, to move your project forward in a efficient manner. All right, talk to you later.